We are going to introduce DRAM in this section. This is an outline of the DRAM section. First, we will have an overview, and then we'll talk about the cell operations based on the one transistor, one capacitor bit cell. And then we'll talk about DRAM fabrication technology in terms of the DRAM cell structure, bunch capacitor versus the stack capacitor, and then the layout. And then the DRAM array architecture, folded bitline architecture versus the open bitline architecture. And then we'll talk about the DRAM scaling challenges in both the cell capacitor and the access transistor. And finally, we'll talk about some recent and future trends of the 3D stacking of the DRAM for the high bandwidth memory, HBM, and then finally some embedded DRAM. So DRAM, is a dynamic random access memory. So here let's understand the keyword dynamic. So dynamic means you have to do this periodic refresh. So this is respect to the SRAM, static. So we're going to discuss the periodic refresh later. This is because the DRAM cannot hold the data forever. So you have to periodically refresh. And random access, again, this is a RAM. That means each bit can be independently read or write. And then volatile memory, again, if power supply is removed, you lose the data. And if you compare SRAM versus DRAM, right, so the SRAM is used for the on-chip memory on the same chip with the processor. So this is for cache. And DRAM is mostly DRAM is off-chip. At the very end of the lecture, we will talk about the embedded DRAM that is on the chip. But most DRAM will be off-chip. And this is for the main memory. And the cell size, SRAM, the minimum you can do like 150, 160 f square, as we discussed before. And DRAM mostly will be like 6 f square to 8 f square. So it's much compact. And then SRAM is faster. You can do that within like 1 nanosecond. But DRAM you have to do like tens of nanosecond, maybe 10 nanosecond to 20 nanosecond, 30 nanosecond in that region. SRAM is non-destructive read. So after the read operation, the state will recover to original state. If you design it well, you make the noise margin large enough, then you will not disturb the state. But DRAM essentially is a destructive read, and you need to recover the data. But this recover for the write-back process, this is done automatically after you read. We will discuss how to do that later. And the SRAM cell leakage current, typically like one SRAM transistor, the leakage is larger than picoN per transistor. But DRAM transistor is a very specialized transistor. It needs very low leakage, less than like femtoN per transistor. So the SRAM uses the logic compatible process, like the oxide is very thin, but DRAM is thick oxide to reduce the leakage and also to sustain higher drive voltage. So this is SRAM is embedded with logic, as I said earlier, come free with logic. So any foundry design the logic will offer the PDK or the memory compiler for the SRAM. But DRAM is highly specialized. So only those DRAM manufacturers can do this. And then let's look at the DRAM subsystem organization. So there is a hierarchy within the DRAM subsystem. On the top will be channel, on the bottom will be the memory arrays row and column. So let's look at what does this mean. So DRAM subsystem, if you look at DRAM, I believe all of you have seen this kind of DIMM called DIMM. This is dual inner memory module, that is a screen board, circuit board essentially. This is called DIMM. It has some controller on the DIMM. And then multiple DIMMs, can be inserted to your motherboard of your system, right? And the multiple DIMMs can share the same data bus. This is called the memory channel. And then your processor can have multiple channels. And then within one channel, you can divide that into different DIMMs. And on the DIMM, you have those black region, that is the chip, and this is packaged chip. So here on this DIMM, for example, you see 8 chips, 8 DRAM chips are packaged and then assembled on this DIMM. And then if you look at the DIMM, sometimes you may have the front side and back side. So this each side sometimes it's called rank. It's called rank. Like the front rank and back rank. Sometimes you only have one side. And then here, for example, you have the 2 ranks, front and back. So here you need to, from each rank, you will get 64 bits out. And then you have a max to select which 64 bits you choose from. Because typically for the DRAM, like DDR, like interface, on this DRAM, so here you see those like pins. Those are the conductive like pins. So there are like 64 of them conduct the signal. Of course, there are some control signals occupied by some of the pins, but there will be 64 pins for the 64-bit data bus width. So here, every time, every cycle, you transfer 64 bits from the DRAM, and each pin give you 1 bit. Of course, there are more pins for the like control and timing and so on, the power. And then if you break down the rank, then you have the 8 chips in this example. And for example, in this case, each chip only give you 8 bits, and then you have to combine those 8 bits to 64 bits for the external data bus. So that means I/O width for each chip is 8 bits in this case, but you have 8 chips, so in total you can still get 64 bits. And if you further break down the one chip into banks, there are 8 banks in this example, and each bank will give you 8 bits. You still need to have a max to select which 8 bits come from. And if you break down the bank, then it will go to the memory like row and columns. So in this example, this bank is 256 megabits. So that means in this case, you have 2 kilobytes, like a number of columns, and you know 1 byte is 8 bits. So in total, you actually have 16 kilo columns. And then in this case, you have 16 kilo rows. So 16 kilo by 16 kilo, you get 256 megabits. So this is like the organization. And then one row is sometimes called one page. At the end of the row, you have this row buffer, basically a buffer or register to temporarily store the data. So I think time's up, so we'll stop here. So at least we have talked about the hierarchy in the DRAM subsystem. So you see those channel DIMM and rank, chip, bank, and so on.